are in lectures 2 for week 3, building upon our concepts developed in first lecture of this week. We now move towards discussion on atomic models that have described distribution or arrangement of electrons around the nucleus. This is very important as actually the interaction of or behavior of electrons, especially the outer shell electrons or the valence shell electrons, results in different properties most of the time for materials, like the electrical conductivity, which is most important property of at least the metallic materials and materials of our interest. We will start from the first model. These atomic models actually deal with structure of atom and then arrangement of electrons around the central part, that is nucleus. In this we have developed classical models. These are called classical concepts, and then we will develop the quantum mechanical, or we will bring in quantum mechanical concepts that update these classical concepts to answer certain questions about electrons and their behavior that were not available in classical concepts. You can see in figure 2.1 shown on this slide that actually depicts or represents the Bohr model of atom, in which there is a nucleus in the center and electrons are shown revolving around nucleus in circular orbits, and these electrons can have fixed number of electrons as per the number of shell around the nucleus. And number of electrons are fixed or remain fixed in a given orbit. Electrons of course can move from one orbit to the other, higher or the lower one, as per absorption or emission of energy from some external source, but given number of electrons that are fixed for a orbit cannot increase. The Bohr atomic model actually took electrons as revolving objects around atomic nucleus in discrete orbits. Position of electron in the Bohr model is defined in its particular orbital. Another important point in Bohr model, this model emphasizes that energies of electrons are quantized as well. This means, for example, for hydrogen atom, energy of an electron from first to second or third orbit is fixed, is quantized. If electron is in first orbit, there is a particular amount of energy that it can have, and if it goes to second, and it must have absorbed some energy from some external sources to move on to the second orbit, and this energy again is quantized. It cannot have more than or less than this quantized amount of energy determined for hydrogen atom. That has been calculated anyways, but we will not go into details. Just you need to keep this in mind. The energy of electrons is quantized, and this energy is as per the orbital energy, energy of the orbit calculated for that particular atom. And these energy levels or states do not vary or do not change continuously in energy values, but these are separated by finite energy values. If you look at figure 2.1, there are 3 shells shown for a nucleus having electrons in these upper shells. So there is fixed amount of energy that electrons can have in first, second or third shells. So the gaps in between these shells, as you may know, are taken as energy gaps. So electrons cannot have energy in between these two shells. They only can have an energy to remain in the first or second or the third or the fourth shell as per the atomic number or the number of electrons of an atom. So electrons in Bohr model can revolve in fixed orbits around the nucleus, and they can have a particular amount of energy calculated for that particular orbital. Moving on to next. The next concept is taken as wave mechanical model, and this model takes into account some quantum concepts that have developed over the period of time. This model, that is wave mechanical model, takes into account wave-like behavior of electrons along with the particle behavior. We know that electron can behave as a particle and as a wave. So wave mechanical model added the concepts of quantum mechanics into the Bohr model, and with this model, electron is not just moving in discrete orbit, rather position is taken as probability of its existing at various locations around the nucleus. For example, if you look at figure 3, which compares Bohr and wave mechanical model of atoms in terms of distribution of electrons, you can see on the left, the A part of the figure, that the position of electron is fixed just like a line. You are seeing that electron can only be along this line in the around the nucleus in the orbit. But on the right side, you see the wave mechanical concepts that shows, that depicts position of an electron as probability of its existence at that position, and this probability varies accordingly. So it's not just taken as fixed position, but it's taken as probability distribution of electrons, and that is taken as electron clouds. So essentially, wave mechanical model when Bohr model just informs about one particular orbit for the electrons to revolve or to be present, wave mechanical model just tells us that depending upon the energy or the interaction, electron can be in a state little higher than this Bohr state, or it may be little less. So it simply distributes one orbit into number of energy states or energy levels within one orbit. In wave mechanical model, therefore, electron is no longer revolving or traveling in one fixed orbital. Rather, there is a cloud of electron locations around the nucleus. This cloud actually refers to the different energy states. If we move on further, here you can see the figure 2.2 on your left. Figure A shows energy levels for Bohr model for hydrogen atom. See, these are fixed. That is the first one for N1, then for particular amount of energy for N2, for N3. But on the right side, figure 2 shows you wave mechanical model in which the first orbit N1, there is just one energy state. But if we move on to N2, one energy level or orbital for Bohr model is split further into two energy states for wave mechanical model, and then for N3, three energy states, and so on and so forth. So wave mechanical model actually adds different energy states for one particular energy level for Bohr model. So what we can say, that looking at figure 2.2 and comparing A and B, energy levels for hydrogen electron in Bohr and wave mechanical model show us for Bohr model only one fixed energy value for electron. If it moves to, for example, third orbit from first, or from second to first, or first to second, whatever it is, depends upon, of course, absorption and emission of energy. Wave mechanical model, however, as is shown in part B of figure 2.2, further splits these higher energy orbits or states into suborbitals or states. This wave mechanical model is characterized by four quantum numbers, 4 parameters that are called quantum numbers, which actually determine size, shape and orientation of electrons probability density for an atom. On the same slide you can see figure 2.6 that shows schematically relative energies of electrons for various shells and subshells. You can see number of things we can determine from this figure 2.6, that the first orbit one state, that is S, second orbit two states SP, third orbit three states SPD, fourth orbit four states SPDF. So these are the maximum number of states SPDF. But here you can also see that for the third and fifth, fourth orbit, that the last state or the third orbit comes actually in between the first and second state of the fourth orbit. So from here we can conclude that energies of the very first states go on increasing as we increase in number of orbits. That is, the energy of the electrons in P state is more than the energy of electrons in D state for the third orbit of atom. And this is true also as we go further from 4th to 5th to 6th to 7th orbit and so on. So we were talking about quantum numbers, the parameters that describe wave mechanical model. Principal quantum number is n, which gives us the number of shell or orbit, and this principal quantum number is actually common to both Bohr and wave mechanical model. This is depicted by small letter n. Principal quantum number. Second quantum number, which is written L. This second quantum number designates subshells, and its value is given by n minus 1. So for example, first orbit n minus 1, n is 1, 1 minus 1 0. So first orbit don't have any subshell. Second 2 minus 1, 1 subshell, the original and the one. So total 2 shells, levels or states, and so on and so forth. For example, second shell, the values of 1 and 2 indicates that shell has 2 possible energy states. Shell 2 is divided into 2 subshells, and so on. Shell 3 into 3 subshells, 3 possible energy states. And similarly, this will go on for higher values of n. The number of electron orbits for each subshell again is given by third quantum number, and that is called designated by ML, whereas fourth quantum number MS, S and L are subscripts for m is associated with spin moment and can have two possible values, spin up or spin down, positive and negative half values respectively. So in short, wave mechanical model added three new quantum numbers giving rise to electron subshells within each shell, and these subshells provide us what we call probability distribution for electrons. By the way, when these subshells appear when we apply magnetic or electric fields externally to the atom. These shells split into subshells at sub-energy levels. Here figure 2.7 shows us filled and unfilled or partly filled energy states for sodium atom, starting from the first orbit to second and to third. This wave mechanical concepts, electron configuration is further determined with the help of Pauli's exclusion principle. This principle states that no two electrons can have same spin in one state. Electrons, when are in lowest possible energy, atom is said to be in ground state or unexcited state, and the electrons present in the outermost shell of atom are called valence electrons. So when we give atoms external energy, they can absorb energy, and electrons move from inner orbits to outer orbits to next higher orbits, and in that case atom is said to be in excited state. With this we come to the end of our lecture. Assalamu alaikum.